Hello, everybody. It's me, Andres, and I'm back again to talk about what I learned about in my Intelligent Agents class, CS 4540, Section 3, in our third week of instruction. Today, I'll be talking about backpropagation. So recall that in my previous video that I talked about gradient descent and how that is the algorithm that we use in order to determine how to best adjust our weights and biases in our neural network. But we didn't talk about how to compute this wild, um, complicated gradient. And yeah, so I'm gonna get into that. So we do this through back propagation, and uh, what this means is when you think about the neural network, and when you think about adjusting all the the numbers that influenced the outcome of your machine learning model, the things that you can adjust and influence are the B's. In this case, B stands for biases. You could also adjust the weights. Here it's represented by W. And you could also influence or change the activation from the previous layer. And the way you do that is by propagating backwards. So, so each of these different neurons here in the output layer have had a cost function that ran through it, and this cost function produces, or yeah, with the negative gradient that we talked about in the previous video. Uh, we have a list of nudges that one neuron can suggest to all of the neurons in the previous layer. So here, what we have is all of the neurons and all of their suggested nudges, um, all of them adding and um, on top of each other in the previous layer. And that's just for one training example. From there, in that hidden layer that we just back propagated into, we can recursively apply what we did in the output layer and further adjust the layers, the weights and biases in the layers beyond this one as well. So uh, that would just be one training example based on one image. In this case, it's a number two. Uh, but we can't just have that one adjustment, that one training example. So we have to run it with all of all of the training data in order for it to be a proper gradient descent. And after we do that, we have all of the suggested nudges to all of the weights from weight 0 to weight 3000. We have all of those, and they average it across all of the different data samples. However, doing it this way, the proper way for a complete gradient descent, is super slow, right? We can't go through all of the training samples every single time. So the way it's actually done in neural networks is through stochastic gradient descent, and what that is a type of gradient descent where you do mini batches of all of the data instead of instead of having all of it. Yeah. And this will provide a significant computational speedup. And the reason is because instead of slowly and meticulously calculating the best way to descend from a given point, as we were previously thinking about it, instead it approximates a direction, the lowest direction, and sort of hops about, and that is the fastest way to get to the local minimum. Or, well, it's faster than doing all of the data. So to recap, what I learned was I learned about back propagation and how each of the nudges that we calculate through gradient descent, how each of those nudges are applied to the layers before them, and then apply to the layers before that one recursively. And the oh, right. And the average of all of the gradients produced by all of the inputs are are what the actual nudge to the weights and biases will be, instead of each model nudging it. And I also learned about stochastic gradient descent, which is a type of gradient descent which, instead of calculating all of these data samples, it just has a mini batch of the data samples, and it significantly increases startup or speed up. And that's what I learned. Thank you for learning with me. Till next week.